Greetings everyone. Now we are going to discuss about the DC characteristics of LED. Okay. The photodetector in the receiver section plays a vital role in the optical communication transmission. Okay. In every receiver section, you will be having a photodetector which directly converts the incident light into the corresponding current. Okay. So it is necessary and vital to study the characteristics of the photodetector. Okay. Now we have here is a OFS module of the PD, a photodetector. Here it is clearly depicted. The circuit is clear, right? We have a voltage bias here, the photodetector here. This is where the port where we are going to connect our optical fiber cable. The light will incident through this port on the photodetector. Okay. And to power up this particular module, we have a DIN connector. As such, we discussed in our optical fiber trainer kit. Okay. To reduce the power fluctuations. We have here three kinds of biases. To study the photodetector, we have three biases here: zero bias, forward bias, and reverse bias. So we will be discussing these three biases in detail. And we have here is our optical fiber power source. Okay. We have two different kind of data here: pseudo random binary sequence and as well as word. Okay, we have an 8-bit word here. 1 byte we can transmit through this optical fiber source, and we can vary the bit rate of the source even. We have here 24 128 till 2048 kbps. We can vary the bit rate of the optical source, and we have here is an optical power meter. In order to measure the power, okay, before incidenting on the optical photodetector, we will be measuring the optical fiber power using this power meter. We have an optical source here. From the source, optical light will be generated, and we will be measuring the optical light power level using this power meter. And after measuring the power level, we will be using this particular kit in the respective zero bias, forward bias, and reverse bias to study the characteristics of the power photodetector. So this is the setup for zero bias. First we are going to discuss about zero bias technique. Okay. Here we have, you have a knob to control the biases. Okay. You have to select the zero bias first. Okay. From the power source, I have connected an ST connector, ST 1 meter optical cable. This is an ST to ST connector we have here. Okay. This is a 1 meter cable, optical cable with 1000 micrometer diameter, and it's a multi-mode cable. We have connected this optical source, powered the optical source. We have here few options like internal, external, and continuous wave. I have selected the continuous wave mode. Okay, and as such we have TTL input and output. Here is a power button, and it is powered by a 12 volt DC. Okay, and this optical fiber is connected to a power meter in order to measure the uh, output power, that is power generated from this optical source. We are measuring using a power meter. We have here minus 60 or around 70 dBm, okay, power, and I am going to feeding this optical fiber, connecting the optical fiber to this kit. Here I have connected a 1 mega ohm resistor as a load. Okay, so by varying this power value, okay, I am going to measure this output voltage using a multimeter. You can see that I am varying the optical power source. Okay, this is the knob here. I am varying this knob. I am varying this knob so that you could able to see the voltage difference in the load across the RL. Okay. Okay, so this is how the voltage varies. Okay, so as we discussed the zero bias, next we are going to discuss about the forward bias. I am changing this bias switch to forward bias. Okay, now it is in forward bias. So again we have to measure the power level first, the power, the light power level, using a power meter. That is, the optical source is generating minus 66.4 dBm here. Okay, so we are going to couple this optical power to this PD module, ensure it is in forward bias condition. Okay, so as we discussed, here we have two different conditions. That is, first we will be maintaining the power level constant and we will be varying the voltage level. Okay, this bias voltage, the bias voltage will be varying and we will be measuring the characteristics of the photodiode. Okay, and then we will be fixing this particular V bias, that is bias voltage constant, and we will be varying the power level. Okay, so these two characteristics we will be measuring in this particular forward bias condition. So with the fixed power level, I am going to vary this voltage bias. Could see the output voltage, that is voltage across RL. This VL is varying, right? So this is what we are going to measure for a fixed power level, how this voltage bias is influencing the detector, that is the photo detector. Okay, and then we are going to fix this voltage a constant and we are going to vary the power level. I am varying the power level here. So I am going to vary this power value. Okay, so you could able to see the difference, voltage difference here. It is at maximum now. Okay, 1.5 we got, and when I am reducing the power level, could able to see this voltage difference. Okay, 1.02, it is 1.0. Okay, so this is how we will be measuring the VI characteristics and power and current characteristics of this photo detector in forward bias. Now we are going to discuss about reverse bias. So I have switched the bias switch to the reverse bias condition. Okay, so now I have fixed the voltage bias a constant first, and I am going to vary the power level. Okay, optical source power level I am going to vary. You could able to see the voltage differences here, right? It is increasing, right? I'm increasing the power level, and by varying this power value you could able to plot the power and voltage characteristics of this photodetector in reverse bias. Okay, now I am going to vary this voltage by keeping the power value f constant. Okay, so in order to measure the power value, I'm going to use this power meter. So it is minus 65 dBm now. I'm going to feeding this light power source, the photo detector. Keeping this power level constant, I am going to vary this voltage bias. Okay, the incremental change we could able to see this voltage fluctuations, right? It is getting reduced, right? So this is what the reverse bias will do in the photo detector characteristics. Okay, this is the power and current characteristics curve when the photo detector is in forward bias. Okay, and comparatively this graph shows the power current characteristics of the photo detector in the reverse bias condition. So as you all discussed, we have three modes here. In summary, I like to quote few points. We have three different modes: zero bias, forward bias and reverse bias. We have measured the power value using the power meter, which is emitted from the power source. Okay, we have used ST connector 1 meter cable multi-mode 1000 micrometer in diameter, and this is our circuit. We have here is a voltage bias, okay, and we have here is a load resistance. This is our circuit. This is our PD module here. Okay, so this PD module, that is power photo detector, is capable of converting this incident light into a corresponding current value. That is, this is what the experiment is all about. Thank you.